what I want to take you through, and it's interesting, I discovered, whoops. I discovered I don't have on my laptop the latest version of Mathematica handbook. But I really encourage you to go to the vector analysis section of the Mathematica handbook. It's incredibly useful. It's got a lot of really good stuff about what we'll be doing. But I wanted to highlight a few features of dealing with things in Mathematica. Something we haven't talked about yet is this idea of loading packages. So particularly with the Mathematica handbook, Peter Taborek has written a lot of very useful tools that solve a lot of problems, and there's no reason to recreate them. It's one of the reasons I have you buy the Mathematica handbook. Now, occasionally, so he had a whole bunch of really useful tools for dealing with vector stuff. Mathematica, in its latest upgrade, made enough improvements so that not all of those tools are needed anymore. So that's kind of cool. Mathematica's finally caught up to them. But it's still useful. And one of the ones that's very useful are a set of tools that allow you to put partial derivatives in a form that looks nice. We'll see that Mathematica uses the subscript notation for partial derivatives that I can never keep straight. You have to remember which of the things is which coordinate, and it just drives me crazy. Deform will put things in a nice form for you. The other thing to keep in mind as we move forward, and this is subtle because it occurs in two different ways, is that the difference between a list and a real vector. So if I want to think in the plane of a point in the plane in polar coordinates, I know the x and y components in polar coordinates. I can write it as r cosine theta, r sine theta. And if I want to make a plot of polar coordinates, I can plot the curves of constant r and the curves of constant theta. And that'll give me the polar coordinate grid. And this was just a cool excuse to show you parametric plotting. Mathematica has lots of different plotting commands, and you really want to look up. It does parametric plots, contour plots, vector plots, and almost everything that it does either as a function, it also does as a list. And so you really want to work through those, and we'll be doing some of them in the class. So xv is not a normal function, right? It's something that's parametrized. That's why we're doing a parametric plot. And we're going to set up a bunch of different curves for us to do it over. And so we're going to generate a table of curves using our substitution. We're going to put in fixed r values, and we're going to plot it as a function of theta. I'm sorry. Yeah, let me say it again. We're going to use fixed theta values, and we're going to vary r in this range. Okay? And so you'll get these curves at different fixed values of r for all theta. Now, one of the things we're also going to use is evaluate here, because if I stick a table inside the plot and I don't do evaluate, I don't get different colors. That's just one of those weird things about Mathematica, and I want to get my different colors. And I'm going to do an aspect ratio automatic because I'm going to add it to another plot later. So, whoops. So this gives us our curves. I do the same thing, switching to fixing different values of theta and plotting for r. And then when I show them together, I get what you hopefully recognize as the polar coordinate system.
Why do you have a giant chunk?
Well, because it gets a little upset if I really do 0 to 2 pi. And so I started at another angle. It doesn't get that upset. I can make that chunk smaller and smaller. And r equals 0, it gets crowded, so it would look kind of funny. So I don't go all the way to r equals 0. It's for aesthetic reasons. Now, notice here's where things get tricky. R theta really isn't a vector, right? It's a coordinate point. If I give you r and theta, I can tell you where a point is in space. X, y really makes sense as either a point in space or a vector, right? So if I give you x and y as a list pair, I can add them as vectors as listed in Mathematica. This is kind of a subtle Mathematica idea. But if I wanted to add a vector where I give you r and theta, I don't add r plus r and theta plus theta. That's not the way you add those components. So I need basis vectors to define vectors in polar coordinates. Now, we know what they are, but we can kind of derive them in case you had some weird one. You basically get basis vectors by taking the tangents to the curves, right? So I have my point, xv, defined in terms of r and theta. So I take the derivative with respect to r, the derivative with respect to theta. Those are going to give me unit vectors in the tangent directions, in the directions of constant r and constant theta. They're not normalized at this point. And so, in particular, it's the theta one that's bad, right, because of the r. The x one's normalized because cosine squared plus sine squared is 1. So I just have to divide by r, and I have now an r hat and a theta hat. And this is one of the things that if you, and we're going to come back to it, but I wanted to kind of lay the groundwork here. If you're going to use vectors a lot in Mathematica, you have to kind of think in this mode of, if I take r hat and theta hat as an xy pair, that now works as a vector. And that takes a little bit of thinking. I'm throwing the idea out here with you now. We're going to practice it some more. But here's an example where it works. And what's even worse is I have a cool thing called vector plot that will plot lines with arrows for me. But it only works for vectors that are a function of x and y. And so by defining my r hat and theta hat, I can then write them as functions of x and y because I know what theta is. And then I can plot the r vectors. I can plot my theta vectors. Those are all my theta hats. And I can put them on top of each other. Now again, with this right here, I don't expect it to make a lot of sense. I'm going to we'll probably either not this week, but next week at some point we'll have some problems to work on in class, where we play a little bit more with these vectors things and how this works. But I wanted to show it to you now. This file's already up on the Mathematica file thing, so you can play with it a little bit yourself and see how these things work and how it works the way you want. But here's why I gave you this warning. When we go to derivatives, things work just a little bit differently. So we said x and y really don't work as the r and theta component because Mathematica doesn't know about r hat and theta hat. And that's true. But let's see what happens when we start doing derivatives. So a few things. You know, there's, like I said, the gradient. And it gives you this weird thing, f10, f01. Well, what the heck does that mean? I mean, if you use Mathematica enough, you will presumably get used to it. But if you use D form, it converts it to what we think it is, df dx, df dy. So what is this? f10 is the first derivative with respect to the first variable, and no derivatives with respect to the second variable, df dx. That's no derivatives with respect to the first, one with respect to the second. So like f11 would be d by dx, d by dy of f. So you have to keep track of it. That's why I like D form. Now, just changing the names doesn't do anything, because Mathematica is about pattern matching. And all it knows now is that we're using Cartesian. Mathematica doesn't care whether your Cartesian coordinates are called X, Y, Q, Susie, James, Paul, Apple, Tomato. It doesn't care. It's pattern matching. As long as it thinks it's doing Cartesian coordinates, it treats this as what we would call the X variable, and this is what we would call the Y variable. You have to tell it, this part I don't understand, but you do have to give it this here so it knows. But if you say to Mathematica, nope, now we're doing polar coordinates, it knows how to do it right. And notice in polar coordinates, we do need that 1 over r to make the units work. And if you were unclear,
Professor,
yeah?
that polar, is that built into the Mathematica, or did you define that?
No, that's built in, and that's the cool thing about the new Mathematica. You used to not be able to do this. You used to have to be more careful and clever with doing gradients. But now it has a list of standard coordinate systems. It has a coordinate system table I'm going to show you in a second. And so you can tell it polar, spherical, cylindrical. And it has a whole bunch of standard ones. Now again, so now we get it, DFDR, 1 over R, DFD theta. I use D form. And again, the variable still doesn't matter, just the order. So if you really like using X and Y for your polar coordinates, you can use X and Y for your polar coordinates. What the polar is telling it is that this second spot is acting as the angle, and so you need 1 over the first spot when you do the derivative with respect to the second spot. It's about pattern matching, and that's a new thing you have to keep in mind. The final piece, or 2 pieces, is there is a command coordinate chart data, and it will tell you things like what it expects the standard names to be. So for spherical, it uses r theta phi. And if you remember, I said theta, we often, in physics, you often see in books that it does we write it r phi theta, where theta is the azimuthal one, a lot of times. But Mathematica does it this way, and you know which is which, because the theta is the one going from 0 to pi. So that's the one relative to the z-axis. And notice, as I said, Mathematica goes minus pi to pi for the phi, not 0 to 2 pi. Now, the final piece I want to say now in terms of using this is, so here's a complicated thing, the curl. And now you can see why, okay, trying to keep track of all your zeros and ones and where they are in the derivatives is a mess. And this is why we really like D form. And this is a case where it really does give you the output as the first one of this is the R component. That's the theta component. That's the phi component. So now if you want to put that together with the piece I said earlier, this is a list of the R component, the theta component, and the phi component. So if I wanted to, so think about this for a second. So what I have in Mathematica is, this was the curl of some function, and it's the R component, it's the curl of some function, and it's the theta component, and it's the curl of some function, and it's the phi component. If I want to then add this as a vector to another entity, I can't just add it as a list, right? Because I don't add the theta to the theta. That's not how I add vectors necessarily in spherical and cylindrical coordinates, because there's other things that go on. I need to turn this into the following sum. So I need to know, that's why I went to the point of showing you the polar hats. So if I write it now instead of a list of 3 components, if I write it as a sum in terms of r hat, theta hat, and phi hat, then I can add that to other vectors that are also a sum of r hat, theta hat, phi hat. And I can keep track of things. And this can be a list of r hat defined in terms of I hat, j hat, and k hat. So that's kind of the tricky multi-layer piece to this, is I can keep track of the components as a list. I just have to know I can't do A plus B as lists. I have to convert them to a sum of things that are actually multiplied by basis vectors. Most likely, I'm going to want those basis vectors as a list that's in terms of I hat, j hat, k hat. And then when I'm done with all my sums, how do you think, so I'd have a sum at the end that's actually got a sum of 3 components that are in terms of I hat, j hat, and k hat. How would I pick out, say, the theta hat component at the end? So I have some final list after doing all my additions. And how would I get v sub theta? How do I get the component of a vector? Dot product or projection. I would take back theta hat, which is also a 3-component list. This is a 3-component list. I would do their dot product, and I'd get a single scalar out that is the theta component. And that is why projection is something you are going to memorize by the end of this class. So that's a little bit for the Mathematica, and we'll come back to it. We are done.